Hi everyone, welcome to Integral Calculus. Today we explore lesson 6.2, volumes by this washer method. Number 1, solid of revolution. Let's say that we have a bounded region, something like this. And we want to rotate this bounded region about the x-axis. Then what do we have? Let's use the GeoGebra to show you guys. This is the bounded region here. Let's take a look at the rotation. Right? We're gonna rotate the region. Done. Oh, we have a solid. This is called it solid of revolution or by revolution. I'll manage to do a copy and paste here. And we have this. Yay. Pretty cool, huh? Here comes the definition of solid of revolution. A solid of revolution is the 3D object generated by rotating a bounded area about a straight line or axis of rotation, meaning that we can rotate about the x-axis, the y-axis, the line x equal 1, x equal 2, y equal 1, y equal 2. Yeah. Most important part about solid of revolution is how do we compute the volume? This is a 3D object, so it has a volume. Let's take a look at how we compute the volume. 2, volume by this or washer method. In A, we're going to take a look at an area bounded by the curve fx between 0 and 4 above the x-axis. In this example, we're going to rotate the bounded area about the x-axis. And when we do the rotation, we're going to get a solid of revolution that look like this. To find the volume of this solid of revolution, we can cut our sample slice, do a vertical cut, and we get a sample slide. Look at the sample slice there. It does look like a disc. So a sample slide, which is a sample disc. A sample disc has the volume of base area multiplied to thickness. Base area is pi r square. Thickness is the small change in x, because this is the slide that is perpendicular to the x-axis. Dx. The radius here is this height. That is the radius of the sample slide, and that is exactly fx. So in this case, we have pi fx square dx. This is only volume of a sample. This, in order to compute the volume of the entire solid, we add them up using a summation equal 1 to n, and it is the sample volume. To get the precise volume, we use the limit as n go to infinity. This is the volume of the solid. Notice that limit of the Riemann sum is the integral. So we integrate this one from 0 to 4. The sample volume is base area times thickness, which is pi times fx square dx. Ah, nice formula, huh? Because we used a sample disk to compute the volume. This method is called volume by disk method. Let's take a look at B. Same exact area. We just have to do a different kind of rotation. Gonna rotate about the line y equal to -2. Yay! And we're gonna have something like this. Rotate this. This is a solid by revolution. You see that there is a hole in the middle. Cut a sample slide. Same thing here. This sample slide gonna have a hole in the middle. Oh, what do we see here? What is this? This is a washer. Ah, a sample slide. It's a sample washer. We calculate the volume of this sample washer. The same formula is base area multiplied to thickness. The base area, you have to be a little careful here. It would be the area of the bigger disk, which have an area of pi r square, and the area of the smaller disk, which have an area of pi the smaller r square. Subtract them and we get the exact base area of the washer. The thickness here is also dx, because the washer is perpendicular to the x-axis. Okay. We can figure out the r square and the smaller r square later when we do an example. I'm just gonna go through the formula here so you see how to set up the integral to compute the volume. Similar to how we compute the volume by the disk method, right? We have to do the limit of the Riemann sum. And the limit of the Riemann sum is exactly the integral. So integrate this one from 0 to 4 of base area times thickness of a sample washer, or volume of a sample washer. So pi r square minus pi r square dx. Yay! And because we use the washer, they just call it a volume by washer method. Okay. Let's take a look at how we do the actual computation here. Ready? 3 examples. In the first example, find the volume of the solid obtained by rotating the region bounded by y equal cosine x, x equals 0 and y equal to 0 about the x-axis. Usually the first thing that we do is that we're going to sketch out the curve and the area. Y equal cosine x, 1, And we know cosine pi over 2 is 0. Right? X equals 0, y equals 0 are just the two axes. So that is the bounded area. Right? Rotate about the x-axis. And we have this one. Right? That is the solid of revolution. It is not necessary to sketch out the solid. What is most important is you have to be able to sketch a sample slide. So a sample slide look like this. It is a sample disk. It has a volume of base area multiplied to thickness. And the base area here is always pi r square. Thickness, well, this sample disk is perpendicular to the x-axis, so the thickness is dx. The radius here is this height, which is exactly y. And then we know y is cosine x. So we have pi cosine x square dx. Okay. Next, in order to compute the volume of the solid, we add them up. The limit of the Riemann sum is, of course, the integral. And so the volume is integral from 0 to pi over 2 of the sample volume. So pi cosine x square dx. Yeah, we can use trig identity here. So 0 to pi over 2 pi cosine square x is half of 1 plus cosine 2x dx. I'm going to move the pi over 2 outside and take the antiderivative of 1 plus cosine 2x, which gives us x plus half of sine 2x, evaluate from 0 to pi over 2. So we have pi over 2, do the substitution. Pi over 2 plus, well, sine of pi 0, so plus 0. And then minus, when we sub in 0, we just get 0. This gives us the pi squared over 4. Find the volume of the solid obtained by rotating the region bounded by y equal x squared, y equal x, and x equal 2 about the line y equal -1. Just have to be a little careful with the sketch here. Let's do it. X, y. So we have a y equal x squared, y equal x. Actually, yeah. And then x equal 2. And as you guys can see, this is the bounded area. Yeah. So next thing is we're gonna rotate this about the line y equal -1. Y equal -1. Okay. When we do the rotation, just be a little careful here. Okay, so here come -2, right? And this is gonna be like this. Have a yeah. We will have a washer as a sample slide. That is the sample slide right here. There's the gap in the middle. Ah, yay! Sample washer. Okay, it's sample washer. Okay, it has the volume of base area multiply to thickness. The base area is going to be a pi bigger R square minus pi smaller R square. Thickness here is dx because the sample size is perpendicular to the x-axis. Now we got to figure out the bigger radius. The bigger radius is this radius right here. Let's see. And what is this radius? So as you can see, it is composed of two smaller part. It's this part right here, which is y equals x squared. And the second part is this one, which is a distance of 1. So pi r squared is x squared plus 1 square. Yeah. Now for the smaller radius, be careful with the gap, right? Smaller radius is this radius right here. From here to here. So similarly, right? We have this part right here, which is y equals x. And we also have the second part, which is plus 1. The smaller radius is x plus 1 r squared, so x plus 1 square dx. Simplify this, then we have a pi and pull it out. X squared plus 1 square minus x plus 1 square, so x to the 4 plus 2x squared plus 1 minus x squared plus 2x plus 1 dx pi x to the 4 plus x squared minus 2x dx. Yeah. And so the volume is integral. We integrate this from 0 to 2 because the region is bounded from x equals 0 to x equals 2. Up is sample volume pi x to the 4 minus plus x squared minus 2x dx. Pi x5 over 5 plus x3 over 3 minus x squared 0 to 2. So we have pi 2 to the 5 is 32 over 5 plus a over 3 minus 4. And then when we sub in 0, we just have 0. 76 over 15 pi. Thank you for watching. I hope you found the content useful. Please like, subscribe, help the channel growth. I will see you in the next video.